This video is about the biocatalysis reaction breaking down Islatravir, an HIV prevention drug. By studying the reaction of how Islatravir is broken down, it's possible to find more effective ways to manufacture it by using the reverse reaction. An enzyme-based pathway is one of the more effective strategies to break down Islatravir into a simpler starting component. The first step is to use a purine nucleoside phosphorylase, or PNP enzyme, to displace the nucleobase with phosphate. This creates deoxyribose 1-phosphate. The next step is to use phosphopentomutase, or PPM, to transfer the phosphate group to the 5 position. Next, deoxyribose 5-phosphate aldolase, or DIRA, is used for the retroaldol cleavage into glyceraldehyde 3-phosphate and acetaldehyde. Finally, the glyceraldehyde 3-phosphate is broken down into 2-ethynylglycerol using the enzymes phosphate transferase, represented as P, and oxioreductase, represented as O. Targeted evolution was needed to favor the reverse reaction to manufacture Islatravir. Examples included a single amino acid change in the PNP enzyme that allowed for a 350-fold increase in Islatravir production. In the PPM enzyme, a library of variants were used. In the end, a D172A mutation and a T97S mutation were used to improve Islatravir production by about 70-fold. The issue the DIRA enzyme was having is that it didn't tolerate high amounts of acetaldehyde. The C47V mutation acts as a regulator to this by binding the product of acetaldehyde self-aldol condensation. The results of this biocatalytic synthesis were a 51% increase in overall yield and a better atom economy. In addition, it achieved the correct selectivity for the desired enantiomer, and it took fewer steps than previous manufacturing methods. This video was made by a group in the Chem 1880 Chemical Biology for Engineers class at the University of Pittsburgh. It was based on a paper by Mark Huffman et al. Titled Design of an In Vitro Biocatalytic Cascade for the Manufacture of Islatravir.